Alright, so we are going to use Scikit-Learn package from Python, and we are going to actually implement what we learned in the lecture, right? So first, I want to just introduce the functionalities that you can find in Scikit-Learn. Remember, in the Scikit-Learn, we have a bunch of libraries, and I mean, usually it comes like a module, and if you need something very specific, you can just import them for your own purpose. So for this experiment, I'm gonna use the Gaussian naive Bayes because there's a reason behind that. This actually assumes that, actually this is also very relevant to what I talk about in the lecture in my slides. It goes back to this idea that the continuous values are assumed to be a normal distribution. So if you have a continuous data type in your column, suppose you have an attribute which has continuous values rather than a categorical value, in that case, yeah, there is no really a category that you can really condition and come up with a conditional probability in terms of discrete representation. So you have to really go along some kind of continuous probability distributions, right? So that's why we need to go back and check the probability distribution, which is assumed to be a Gaussian distribution. Okay, so I'm gonna use this model with the assumption that my column, my attribute, is normally distributed. At this point, maybe you should not really worry about that much, but in the future, if you are going to deal with other data sets in which you can have data in a column which doesn't really comply with normal distribution, suppose it is more suitable to multinomial distribution, or you can have a Bernoulli distribution which fits very well, or you can have categorical one, which is the one I actually really talk about during my examples, during my lectures. This is more like a default. I mean, this is the default way we actually talk about. But again, it really goes back to some kind of ratios and other stuff. So you should not really worry about all these things at the moment. But in the future, if you happen to deal with different data sets in which you observe different data distributions for your columns, in that case, you might think about, okay, which model or which distribution you have to consider. Okay, baseline is like the bottom line is basically these are all make an assumption that your column has a probability distribution. So when we calculate our conditional probability distributions, we are going to just assume that, hey, my data is distributed with this normal distribution. It has an average value, which is a mean basically, which has a standard deviation. So based on that, we are gonna just get the conditional probability distribution for my instance. So I'm gonna just assume that I have a data, and then for a given data point, I'm gonna try to estimate or make a prediction which class it belongs to. Okay, based on this conditional probability distribution. All right, long story short, I'm gonna import this Gaussian naive Bayes because remember my assumption is this data column is distributed normally. Okay, that means Gaussian distribution. Okay, I mean Gaussian distribution, normal distribution, these are the same things, right? So in case you forgot those things, let me remind you that. Okay, so the guy I'm gonna need is gonna be this in specific, but the way you are going to import this is gonna follow this line. So you basically go to the module which have all the Bayesian models. From there you just import this guy. You could have import everything that you have, but specifically we are going to use this in our experiment. Therefore I prefer to just get this guy out for my experiment. All right, so I didn't have to deal with the iris data set, but for the sake of illustration I'm gonna talk about iris data set. Normally when you read your data, they don't really exist in the data sets which are in the repository of Scikit-Learn. So we'll have to read our own data. So in this case, I just load my data, iris data set. If you recall, if you have watched my earlier lecture where I was explaining this, I told you that one portion of this data set is the attributes, another portion is the class labels, right? So these are for class labels, these are the attribute values, and these are all numerical values. That's why we try to fit a NaiveBayesian model which comes with a Gaussian model, okay? Because we have an assumption that these are all continuous values, and we also assume that these are normally distributed, okay? That's why we employ this idea. Yeah, usually we do assumptions. We assume the things and then we move forward. I cannot really guarantee that, hey, this data is normal distributed, and you can argue that how come you can know if a data column is a part of a normal distribution. You are absolutely right about that. But we are just making assumptions because we are making approximations. When you do approximations, this way or other, you may need to make some assumptions, and we are going to follow those assumptions in this case. Anyways, so remember, my GMB, it is just a name I gave. It is just an object I create over here. It's an instant, I would say, and there are no parameters. But if you would like to fill the parameters, you can just go through the parameter list and try to change them. But at this moment, again, you don't have to deal with that. So this part, I fit a model, and then on the fitted model, I try to make a prediction. Well, I could have done the following. Let's say model, and I could have just say, hey, fit a model for this, okay? And then I could have said y prediction is model predict. You see, as I type, it will just try to appear, and I'll say iris data. Well, you may be curious about why I put iris data one more time over here. It is just for experimental purposes. Normally in the real life, you would have something else over here rather than the original data. But I'm going to use this opportunity to illustrate that you can still use your original data to make a prediction to see what is your training accuracy and other things, okay, such as specificity, sensitivity. Okay, we are going to talk about those things, but yeah, let it stay there. So you basically train your data, and on the train data you try to predict the same thing. So you use the same data to train and to predict. Yeah, this has nothing to do with the real world validation or test. I'm just trying to make an assessment about my training stage. I do a training, and then I just try to show how well I did in my training stage. It just gives an idea about training, nothing more, okay? Again, you could have them in two pieces, or if you want to make in a shortcut, you could have them like this. Both will be okay. So I can just enter Control and Enter to run this line. So you see I have a print statement here, and it says, hey, this is the when I say data shape is a feature for a data frame. You can it will give you two numbers. One is going to be number of rows, other one is going to be number of columns. If you just say shape 0, that means you are referring to the number of rows. Number of rows in our context will represent number of data points, right? So looks like I have like 150 data points, and here I'm just doing a quick check. These are the actual class labels, and these are my predicted class labels. I just make a comparison neck to neck. If any of the corresponding labels are equal to each other, it's gonna turn true, otherwise it's gonna be false. Just assume that true values are represented with 1 and false values are represented with 0. If you sum them up, you will end up getting the true values. Okay, that's why, again, these are not really related to the course curriculum. I just try to introduce those those things in case you want to excel in Python and or in Pandas, you know, in this kind of environment for your data science projects in the near future. Okay, so this was a Toy Story 5 maybe. Okay, it was a joke, by the way. So in this case, I just learned how to import a library for my Gaussian, for my NaiveBayesian model, and I had the assumption that it's going to be a normal distributed data for that specific column. I just load and toy data. I fit a model for this guy. So model is the thing that is basically something that you train by yourself, and then you try to make a predictions over the feature data. Again, for a feature data, they have to have the same number of columns, by the way. They can be any number of rows, any number of data points, as long as they have the same number of columns. So they have to comply, they have to match with your current data structure in terms of the number of columns and so on. Okay, so make sure that you are doing things correct, so they have to agree with each other in terms of dimension and data type and so on. And then I just do my prediction. So it was it for a built-in data set, but normally people won't provide you some built-in data sets, right? In that case, you'll have to read your own data and do your training by yourself. So here I'm going to illustrate one more time. I remember I did this another time, but just to refresh your minds, I'm going to introduce this guy so that it can recognize your drive on your Google Drive. Okay, if you do not have this, then you won't be able to use your own data that is stored in your Google Drive. If you don't want to really type this, if you cannot memorize it, which I really understand, I don't even, I am also sometimes lazy about it. You can just click on the mount data and it will refer to this cell. If you do not have this cell, let's assume that I don't have this guy. All right, suppose I wanna mount the drive. In that case, it will create this cell for you so that you can have this line in place. So I'll just run this. Okay, and yeah, in my case it was already mounted, but in your case probably it will drag you another website for your Google for your Gmail credentials. So you are going to make a copy and paste, and it will just confirm the credentials. It will let you use your drive. So looks like everything is in place. So you can just do refresh if you cannot see your drive over here. So this will behave like a Linux machine, right? Linux environment. So it has the bin folder, it has the home folder, you know, it has the root and so on. All right. So what you need to do is that you need to go to the content to be able to reach your data. Under the content, that you can see some sample data. These are coming from Colab, but you have to get into Drive to be able to see your own drive. So in my case, I'll go to my teaching directory. So there are a bunch of courses I'm teaching, and then for this course, I go to my data folder. So I just go and select this guy. I just copy the path of this guy. Okay. I go through this practice just because sometimes it is kind of hassle how people put those things in place. So you cannot really know the whole path because you would never imagine that you are dealing with a Linux machine or something like that. Rather than doing that, you can just copy that path and paste over here. So you see I was able to do this, and I'm gonna do the same thing for my test data. So instead of saying train, I know that I have test data too. So this first line will read my training data, second line will read my test data. You don't have to do like this. All right, you can always read a file into a single variable, and you can split the data because that variable becomes a data frame. But for the sake of, again, simplicity, I prefer doing like this. But normally in the real life, when people pass data to you, probably you are going to need the single file, and then you'll split your data into training and test inside your code, because people may not really provide you some train test and a test separately. Usually it comes in a single data set. like I provided you guys. But notice that I'm reading a CSV file which is a function in this PD library. So first you import pandas, but I don't want to write pandas over and over. Instead, I just abbreviate it like PD by using the as keyword. Probably you are familiar with this guy. So you can do with any library in Python, by the way. You can import, let's say, a NumPy, and you can just say as MP. All right. I'm gonna remove this because I'm not gonna use it right now. So suppose I read my, I run this row, I run this cell, and I just read it. There is no error. And here I just wanted to show you, hey, these are my column names. I just wanted to show all this. Again, this is slicing. So I just wanted to show you the column names. Looks like I have all these things, but this will not include the label. If you want to make this 9, then in this case, you are going to see that that last column is the class. In Python, remember, when you do slicing, the number that you put is not going to be the last index. Basically, it is n-1 will be the last. And so this number is not included in your call. All right, so let's get back to the very exciting part of this exercise. So it looks like I have the data. I'm gonna go through the same practice again. All right, so I'll just create a CLF for classification, or if you do not like this, you can just say model. All right, which may make more sense to you guys. And then for the model, I go and call my fit function. So let me also replace it with model, which will make more sense. So what I'm gonna do here is that in the training data frame, this is a data frame, right? Because as soon as you read the file, it becomes a data frame. So this is based on the numerical indexes. It will just slice your data. So you can have those individuals and change those things into 8. Okay. So what I'm gonna do is I'm gonna use my between those indexes I have my attributes, right? Okay, if you count like 0, 1, 2, 3, 4, 5, 6, 7, so you have like 7 of them, right? Between 0 and 7. Now, these are the indexes, by the way. You will see those are the attributes that you are going to be using. So it starts from 0, it ends at 7. It starts from 0, it's going to end at what? I'm sorry, this is the last column. All right, so this is basically the index is 8. So this second part is the label, by the way. All right, so you train a model. You can still try to make a prediction for your model. If you want, we can also do that. All right, and suppose you are providing the test data. You see the same structure follows. Number of data points might differ. Indeed, there are like 18 of them. All right, so there are 10 of them, not 18. So I'm gonna fit the model. So I'm gonna use the model to make a prediction, and whatever I predict will be y predict. This will be like a one-dimensional array. It is basically it is gonna be a one-dimensional array. Okay, let me run this very quick. So you see I have an array. It said, hey, the first one I tested negative, second one I tested positive, third one I tested negative, fourth one I tested predicted positive. So these are all predictions from the model. And now it is time to consider our accuracy in terms of number of true positive, number of true negative, and false positive and false negative. So we are gonna do that. So 6 is the true negative. That means there were like okay, false positive and true negative, they are actual total number of negatives. So it looks like there were like 7 negative cases, and out of 7 I was able to predict correctly 6 of them. And there were like 3 positive cases. How do I know this? Because there is a false negative for one, true positive for 2. That means there are in total 3 positive, but one of them, I missed one of them. I said, there was a patient who has the disease, but I told the patient that the person is healthy. So I missed one of them. So these are misclassified instances. So you see, out of 10 instances, I missed 2 of them. That also means that I was able to predict 6 plus 2, which is 8 out of 10 correctly, which is an 80% accuracy. Okay, so this is my prediction accuracy. If you want to go back and do the same thing that you did in the iris data set, maybe we can open another cell over here. Oopsie. Okay, I mixed up the shortcuts. Okay, what was the shortcut for this? Okay, let me use this guy. Okay, this is Mac and things are sometimes gets complicated. Okay, so I can just use my, okay, I can say, let's say train predict. So I'm just coming up something new, right? So I have the model, so I'm gonna say model predict what. So you see, I'm gonna get this guy, I'm gonna get the training data set, and I'm gonna make a prediction. Okay, so I'll get this prediction. So it did some prediction, but I didn't print anything, right? So these are my predictions for this guy, and I can use the same thing over here, okay, to do some sort of training accuracy. I just want to see, I'm just curious about it. Okay, so these are the true these are the predicted values for me. So I'm basically doing this spontaneously, sorry about that. So oopsie, train predict, and then so why true, these are the true values. So you may want to visit your training data frame, and you can get whom, you can get the last column over there, which is the 8th one in terms of index. So you can run this. Okay, so look at this. So in terms of the training accuracy, I missed that many cases, but in terms of the accuracy, 416 plus 161, which is 577, right? I don't know out of what, so you need to sum up all the numbers, right? So maybe I can just quickly go to R, and I can do some kind of, or I can basically use this same window here. So I can do the following basically. And it's a good practice though. So I can just have all these things. So you see true negative plus true positive, right? So yeah, here I'm just trying to see my accuracy. I'm just trying to show you my accuracy. That's the only goal. But this is, again, this is training accuracy. I'm trying to show you guys. Okay, so it looks like I have 76 training accuracy. If you look at this, I have 80% test accuracy, which is good. This is a good scenario though. Like, I mean, this is better than having a very high training accuracy and very low test accuracy. Remember, when I first talk about the decision trees, I talk about something called overfitting. What was overfitting? Overfitting was you basically try to handle everything in the training stage. You try to build a very perfect model because you are trying to handle all data points, and in the training stage you end up with a very high accuracy. But when you really test your model in a test data, then your model can most likely fail. It is just because you really overfit your model to be able to handle all the training points. When it comes to real data, it may fail to make correct predictions. But here we have a relatively nice scenario because it is the other way around. In the training stage you have a lower accuracy, in the testing stage you have a higher accuracy, which is nice though. Usually testing accuracy are lower than training accuracies in general. I mean, based on the experience, I would say. But this is, you can have the other way around, because it really depends on the data. Anyways, I hope you enjoyed this part of the lecture too, and please go back and check the training decision tree. Try to see how these two models performed. So you can do a quick comparison between decision tree and naive Bayesian model that we built today. Please go to the other one. It is also in Google Drive, right? So if you go to the Python scripts over here, open this guy and try to see what's the accuracy over there, what's the prediction accuracy, I mean, and then make a comparison between these two guys. Okay, compare this guy with your naive Bayesian model. Actually, you see the comparison. Actually, naive Bayesian perform better than the other one. So decision tree missed one more negative than the naive Bayesian. Anyways, I don't want to make this really long for you guys. I hope you got the idea. Please try to experiment those things by yourselves. Okay, let me stop here.